So we do forms of science in our everyday life without even thinking about it. If you think about when you go shopping and you're looking at brand A versus brand B, you do some steps that are similar to scientific methods. So like you're asking questions, which brand is better, which brand has more in the product or a bigger quantity. You're making observations, you're analyzing data, and then finally you draw conclusions. So the goal of science is to gain knowledge about the natural world, starting with a question, and then tries to answer the question with evidence and logic. An exploration of all the whys and hows that any curious person might have about the world can deal with science. So to understand the natural world, scientists have to make 4 assumptions. The first assumption is that nature can be understood through systematic study. This means that when scientists study nature, it is logical, it has a process, and these processes that scientists are trying to replicate are assumed to be the same processes that occur in nature. The second is that scientific ideas are open to revision. So as science progresses, we get new evidence or new data. And this new evidence will allow or can allow scientific ideas to be updated and revised. Sound scientific ideas withstand the test of time. So that means that even with constant repetition of research, there are some scientific ideas that don't ever get new evidence, kind of like gravity. We will always watch objects fall in the presence of gravity. And then lastly, science cannot prove or provide answers to all questions. So scientists have to be okay with the unknown and not being able to answer every possible question. And we'll get into that in a little bit more. So first of all, nature can be understood. Nature is thought of as a single system, and it is controlled by natural laws. These laws are not influenced by humans. So a scientific law is a statement that describes what always happens under certain conditions in nature. And a way to remember that is law ends with W, just like what starts with. So for example, the law of gravity states that objects always fall towards Earth because of the pull of gravity. This is explaining what is happening. Sir Isaac Newton was the scientist who created this law or first began to develop it. And this could explain many natural events. The second assumption that scientists make is that scientific ideas can change. So science is a process rather than a set body of knowledge. So this process is constantly changing and adding new information. So we're always testing and revising ideas as new observations are made. Ideas may be challenged or replaced with new ideas that better fit the facts. So for example, Einstein's theory of relativity didn't throw out Newton's laws of motions. Instead, he showed that Newton's laws are part of a bigger picture. So this is kind of like science that was done a long time ago as the building blocks or the foundation for new scientific discoveries today. Scientific knowledge can withstand the test of time. So 200 years ago, John Dalton, you may remember him from talking back in 9th grade, proposed the atomic theory. And the atomic theory states that all matter is made up of atoms. And this is still valid today. So this is withstanding the test of time. Something 200 years ago is still valid today. And lastly, The fourth assumption that scientists make is that science cannot answer all questions. And so what's important to remember is that science relies on evidence and logic. And it only deals with things that can be observed, because the only way to get evidence is through observations. So an observation is anything that can be detected either through human senses or with instruments and measuring devices that extend the human senses. So like a microscope extends the human sense of vision. So supernatural beings or events are outside the bounds of science. And so this usually deals with religion. And so, for example, did life on Earth evolve over time? This can be answered by science on the basis of scientific evidence and logic, such as fossils. We can observe fossils of organisms that once roamed Earth. We can do radiometric dating to determine how old an organism was when it died. The question, was life on Earth created through another method, cannot be answered through science because we don't have a way to observe it. So could be a matter of belief, and therefore this is outside the realm of science. So when scientists, quote unquote, do science, they tend to use the scientific method as a guideline. And so as we go through talking about the scientific method, it's very important for you to remember that there is no single scientific method. So the scientific method is more of a guideline than a set in stone kind of rules. So these are the 6 steps of the scientific method, and scientists can do them in any order. They could repeat steps, or they could totally skip steps as well. And so the scientific method incorporates scientific investigations, and this is a plan for asking questions and testing possible answers. So how are we going to actually come to a conclusion? So the first step of the scientific method is to make observations. And so if we were to look at this picture of a moth, you could observe that there are some eye spots on the wings. So like here and here. You could observe that it is a brown or tan colored moth. And there's many, many more observations. If we were making observations in real life and it wasn't a picture, we could maybe describe how it feels. Is it feathery? Does it feel brittle? Is there dust coming off of it? So those are types of observations to make. Your second step is to ask a question, because your observations are going to lead to questions. So a question could be, why are there eye spots? Or why is the moth tan in color? And so all of these come from your observations. Next, we have to form a hypothesis. And a hypothesis is a possible answer to a scientific question. And it's not just any answer. The answer must be based on scientific knowledge. And scientific knowledge means that it came from logical testing. It wasn't just what somebody thinks could happen. And it must also be logical. It also, most importantly, must be falsifiable. And this means that it can be shown as wrong. So we can show that hypotheses are incorrect, meaning our hypothesis, our possible answer could be wrong. And so it must be possible to make observations that would disprove the hypothesis. So let's assume you know that some birds eat moths and that owls are one of these birds. So from this knowledge, you reason that eye spots scare away birds that might eat the moth. And so from here, you can test your hypothesis. Before you test the hypothesis, usually scientists make a prediction. And this is a statement that tells what will happen under certain conditions. So for example, the general format of a prediction is that if A occurs, then B will happen. So based on your hypothesis about moths, we could say if a moth has eye spots on its wings, then birds will avoid eating it. It's kind of like a cause and effect statement. Next, we have to gather evidence. Evidence is any type of data that may either agree or disagree with your prediction. So this could be based on more observations, such as observe moths with eye spots, and that birds really do avoid eating those moths. And you could maybe have a sample of moths without eye spots and count how many moths without eye spots get eaten compared to moths with eye spots. The next part of the scientific method is to draw conclusions. The evidence that agrees with the prediction and supports the hypothesis. So in our particular case, the hypothesis is never proven as true. We don't like to say the word proven because that kind of indicates that it can't be disproven, never ever in the future. So maybe sometime down the line, life events or natural events could change, and now the owls have figured out that the eye spots are pretty well meaningless, and they will start to eat the moths with the eye spots too. So all of the possible evidence on Earth or in the world or in the universe can never be examined, and one day evidence could possibly be found that disproves your hypothesis. And so we generally say that a hypothesis is supported by data, and that it could someday be unsupported by the data. Finally, scientists will communicate the results. This allows others to test your hypothesis. If researchers get the same results as yours, they add support to your hypothesis, and the more and more support you can add to your hypothesis helps it become more accepted in the scientific community. If they get different results, they could disprove the hypothesis and could require then further testing. So when sharing results, scientists will always describe their experimental methods and point out any possible problems. And so in doing this, scientists are very transparent in how they do their experiment, and they're very honest about possible mistakes that they made, shortcomings in their research, so that way they can be held in high regard in the scientific community and call for extra research wherever their shortcomings would be. So, for example, while you were observing your moths, your presence may have scared away the birds. And so you being out in nature could have deterred the birds from eating the moths. And this is where we introduce error into the investigation. So a lot of times science teacher especially, is what would you do differently with this experiment to minimize the amount of error that you have in your experiment. So an experiment is a special type of scientific investigation that is performed under controlled conditions. And so we've spent some time talking about independent and dependent variables. The independent variable is the variable that affects the dependent variable. This is the part of the experiment that the scientist manipulates or changes, and there can only be one independent variable. The dependent variable is the affected variable, and this is the outcome or results of the experiment. When we look at errors or shortcomings in scientific experiments, we could look at sample size and repetition. The sample of an experiment consists of the individual or events that are being studied. So usually your sample size is smaller than all such individuals or events that exist in the world. So maybe I'm doing research with the school, and I only choose to sample or run the experiment with the 10th grade, whereas if I used 7th, 8th, 9th, 10th, 11th, and 12th grade, I would have a larger sample size. So whether the results based on the sample are true in general cannot be known for certain, and so the larger the sample is, the more likely it is to represent the true results. The more times the experiment is repeated and the same results are obtained, the more likely the results are valid. This comes in with the communicating piece of the scientific method, allowing other scientists to replicate your experiment, gives you that repetition and hopefully the same results. Other types of scientific investigations, sometimes it's almost impossible to do experiments. And so, for example, scientists studying an extinct animal cannot experiment with that animal because it no longer exists. So scientists must rely on evidence in the natural world, such as fossils, in order to draw their conclusions. Natural studies are studies that are done in nature, and this shows what actually happens in nature versus what happens in a laboratory. They may provide a truer picture of what happens in the real world. Tricky things about natural studies is the scientist cannot control factors that might affect the variables in the investigation, and it makes your observations more difficult to interpret. There are no controls to help determine which of the many factors explain the observations. So, for example, if you assume you are studying how plants grow in a forest, you can't control the amount of sunlight or rain a plant receives. And so you might not ever know the exact right answer to your question. You probably will get close, but there will always be some unknown or uncertainty with your results. Modeling is another type of scientific investigation, and a model represents a part of the real world. It's often much simpler than the real world, and it's very useful for studying complex systems. So a model generally takes a complex system and looks at just a small portion of it in order to simplify it. Models must be evaluated in order for them to, in order for their effectiveness to become understood. So we want models to represent the real world as accurately as possible. We want to know any limitations there are within the model, and then how useful is it? So the usefulness will depend on how well it's able to predict events of the real world. And so we use models all the time when we predict the weather forecast. So sometimes you may hear that when we're in winter and the weatherman says that, well, according to one model, we should get 5 to 7 inches of snow, but in a second model, we'll only get 1 to 3 inches of snow. So these are constantly evolving and changing in order to best predict the situation. So even when a model's prediction matches real-world observations, it doesn't prove that the model is true or that it is the only model that works. It just means that the model supports events in the real world. So another example of a model would be a food chain. Food chains represent complex systems in nature, and it makes systems easier to understand. Models help us, or this food chain model helps us see how energy travels from the producers in a system all the way to the top predators. Lastly, we have scientific theories. And scientific theories are broad explanations for events that are widely accepted as true. So in order for something to become a theory, a hypothesis must be tested over and over and over and over and over again, and then be supported by a ton of evidence. So, for example, the theory of evolution, the cell theory, and the germ theory are all theories that have been tested, and every time it gets tested, the evidence supports the previous evidence. And so there currently is nothing, or has been nothing has been discovered to disprove any one of these theories. So outside of science, people use the real world theory to describe a guess about how or why something happens. But a scientific theory is more like a fact than a guess. And so it's very important to be okay with the idea that scientific ideas are always changing. And they're always changing as new evidence is being discovered. And so part of being a scientist is being open-minded to that change.